Okay, for today's talk, I'm going to talk about, as you see from the title, something which has two parts to it. There is the second Born electrons, which has to do with using the second Born approximation in doing electron scattering from atoms. So in particular, there's a very curious thing involved here in what I'm going to discuss, where the Born approximation is a perturbation series where the second term actually dominates over the first term. And that already is interesting, and it has to do with a particular part of electron atom interactions where an ion comes and hits a neutral and captures an electron. So it becomes the neutral, and then the A is ionized. So this is called charge transfer, and in particular into the forward direction at high velocity will be what I'm going to talk about, because there's some peculiarities about this particular thing. But I will talk a little more generally about electron atom scattering, because that's a very important part of how we learn about electrons and atomic dynamics, and also has many, many applications. So that will be the substantial part of the talk. And then there is the second part of the rescue at sea. And it turns out that there is a maneuver when somebody falls overboard at sea for the most efficient way to turn the ship around and actually rescue the person who has fallen overboard. And I'll start actually with that. And in a very interesting way, you will see that actually this is somehow connected with the second Born approximation of quantum mechanics. Okay, and so that's what the talk is going to be about. So in fact, let me start by introducing that second subject. And of course, at the end, I'll come back to it to show you the connection. And it stems from an article that I was reading called The Ships of Port Revel in a literary and political monthly magazine, and it was written by John McPhee. Now, some of you probably will recognize the name because he's a very interesting man himself. He has written a variety of books on geology. Now, he's himself not a geologist, he was just a writer, and he is now in his 90s and still writing. So John McPhee had an article which I was reading, and it had to do with a training of ship captains and ship officers. And so there's a school for this, and at that place called Port Revel in France, they train these people. And one of the things that they do is something that was originated in the 1903 Russia-Japan War, which itself, interestingly, actually has many historical aspects to it. It's the first time, actually, that an Asian power actually defeated a European power in that 1903 Russia-Japan War. But a Russian sailor called Butakov came up with a maneuver on how to turn gunships, which are firing on the shore. And so, of course, what you want to do is turn it around, and then the guns on the other side of the ship can fire on the shore. So the question was, how do you most efficiently turn the ship around so that the other side, which is being reloaded in the meantime, is going to fire on the shore? And so this man, Butakov, came up with this method. And it turns out that independently, it was invented again in World War II, in the Pacific War, when an American officer came up with the idea of how do you rescue a sailor who falls overboard. And it's the same maneuver, and you will see the connection between these two and the second Born later on. But let's look at the maneuver, and the maneuver is actually a very interesting one. And that is that I think many of you know that a big ship, like one of these big container ships of today or a battleship and so on, it's extremely difficult to bring it to a stop. And so the best thing they do is, of course, to reverse the engines, but still it takes a very, very long time for such a ship to come to a stop. So if somebody has fallen overboard, you want to come to a stop and turn around, that is really not a very good thing to do, because the braking has to do, of course, with the acceleration, and these accelerations are extremely small for a big ship. It's actually interesting to put in some numbers. So if you think about g as a standard acceleration with respect to which we can think about, so you see that g is about 20 miles per hour per second. So in our cars, for instance, if you're going at 20 miles per hour or 36 kilometers per hour or something like that, you can come to a stop very quickly. You jam the brakes and in about 2 seconds, you will have stopped. And that's because the accelerations or decelerations are roughly of the order of g, slightly less, maybe a half g or a fifth of a g, but they're of the order of g. The same thing when a plane takes off. You have to reach speeds of about 200 kilometers per hour on that runway. And again, if you work out what kind of acceleration that is, it's a little smaller than g, but it's of the order of g. However, if you look at a ship, and in fact, first time you actually put in the numbers, which I did for preparing this talk, you're startled by how poor ship decelerations are. There's something like 2 or 3 orders of magnitude smaller. And this is the reason why it's extremely difficult to bring a ship to a halt, turn it around, and come back. So what both Williamson and Butakov suggested was the following. Let's say, for instance, you are at this point and somebody has fallen overboard, or you want to turn the ship around so that the other side is facing that shore. Then the idea was, don't reduce the speed at all. Keep maximum speed of your engines, but you make a very rapid turn of the wheels. So of course the ship is going to start swinging around. And then as it swings around, the maneuver says that when it reaches roughly 60 degrees to the initial direction, now you rapidly turn the boat around in the opposite direction. And what you will end up doing, of course, you will make some kind of a loop. And then you will end up, of course, downstream, but now in the opposite, facing the opposite direction. At all times, you maintain the same speed v. Okay? So you've just reversed the velocity, basically, from here to there. And it turns out that this actually is a more efficient thing to do than to try and come to a stop, which will be way down, and then come back. Okay? And so this is the Williamson-Butakov maneuver. And it's fairly easy to state. And in particular, I want to emphasize here, and you will see the connection, of course, as I speak, that you do this sort of 2 turns, and there is this roll of 60 degrees. And let's see how this connects to physics. So now let me turn to the idea of perturbation methods more generally than the particular context I will, of course, discuss. And perturbation methods, of course, we know are used everywhere because there are only a few exactly solvable problems. And then we always say that if you can solve some dominant piece of the problem, and then you take other effects into account as weak effects. So perturbation methods are very, very old. They start with physics. Newton himself, of course, realized that the two-body problem is exactly solvable, but as soon as you bring in other planets or moons or so on, it no longer is. But on the other hand, you might think that these are going to have smaller effects on the planet than the main sun, and therefore he developed perturbation techniques already then. And of course, when it comes to quantum mechanics, the same story. So for instance, the hydrogen atom is exactly solvable. We do it in all our classes. But then add even one electron or add a field, an electric or a magnetic field, and suddenly it's no longer exactly solvable. Even a very simple thing like that in an atomic system. So of course, what we think of is that there is some part of it which we know how to solve, and then the rest, let's say, is in some ways weak. And of course, we're going to then develop a way of calculating, say, corrections to energy, or maybe some transition from some nth state of the atom to the mth state, and so on. So there'll be a dominant piece which you get from the first unperturbed part, and then you take into account in some manner, it's some kind of an averaging, if you wish, of the perturbation itself. And of course, you can see that you could take that into account to first order, which means just once the H prime appears, or you can have it go to the next order. And you're, of course, hoping that these things will get smaller so that it makes sense to do that. And of course, that is what we mean by a perturbation series. Now, is this meaningful? The test is, of course, are the successive terms getting smaller? If you want to be more rigorous, is that series even going to converge? These are all questions. I won't really get into any details of it. I've just noted here that even the question of a simple electric field, a static electric field in the hydrogen atom, people calculate these things to very high order. And actually, the series does not converge in that particular example. It's very clear, the physics. But as I said, I don't want to go into it unless you want a question at the end. And the perturbation series actually diverges. But at least you do these calculations to some order, hoping that the first and the second term and so on will give you what you're looking for. And then, of course, there are the famous field theories. The most successful from the beginning has been, of course, QED, where there's a natural parameter, the fine structure constant, which is about 1%. And therefore, again, you hope that as you go in powers of that, the series, the terms are going to get smaller and smaller. And this is how all calculations are done. Again, whether the QED series actually converges is an open question. In fact, actually, it most likely doesn't. And like in most field theories, you find that these are usually divergent series. That's the best, in a way, that we can do. Now, of course, there are examples, and we see this right away in our first courses in quantum mechanics, that the lowest non-trivial order is what you want to go to, because the first order sometimes may just vanish because of some symmetry considerations or something. Then, of course, you have to go and calculate the second order. So certainly we all learn when we learn perturbation that we go to the second order to be able to calculate, for instance, the correction due to the electric field on some excited state of the hydrogen atom even, because the first order term vanishes. Now, usually there are then the lowest non-trivial order means that there are some selection rules. So for instance, in atomic transitions, it's the electric dipole. And so if you think of the hydrogen atom, for instance, if you're in an excited 2p state, it is allowed by all these selection rules to go down to the 1s state when it interacts with the electromagnetic field. So that's the first order, you can calculate that. That's your famous Lyman alpha transition, important throughout astronomy, the 1216 angstrom transition. And it goes, the lifetime for that, this is a so-called allowed transition, an electric dipole transition. The lifetime is of the order of a nanosecond. On the other hand, there's a companion, as you all know, to the 2p, which is the 2s state, which by selection rules cannot do that. It's not allowed to decay by the electric dipole, and actually it turns out that the only way it can do it is in a 2-photon transition. Again, not necessary for my talk today, but it's a much, much longer lived. So notice that the time for that decay is 1/7 of a second. So it's 9 orders or so different from the allowed. And this is typical. When you have to go to a higher order, you're going to see it much smaller, and this is why many times we can stop with the first non-trivial order. Now in scattering, which is going to be the title, going to be the subject for this talk, there is the Bohm approximation, which is used widely throughout all areas of physics. And almost always, it's of course going to be the first term, this got cut off, of a series. It's again a series. So there'll be a Bohm, first Bohm, a second Bohm, and so on. And typically, one calculates as much as one can, because the calculations get harder and harder as you go to higher and higher orders. So in scattering, the Bohm approximation, it's almost always the first term that dominates. And that's the one that we deal with. Now, here's, just for interest, this is a picture of Max Born, roughly around the time that he did this work. And this is actually a photo I put in for interest here, because maybe some of the younger students in particular won't know that Max Born actually spent about 6 months in Bangalore. And this is he and his wife, the wife in a sari there, in 1937. And there was even some consideration that he might want to stay, but he didn't. He stayed about 6 months, and then, of course, he was fleeing Germany, and he ended up in England in his case. As you know, during the Second War, many of the German physicists, of course, fled to other countries, and Max Born, for a while, was even considering settling down in India, but he finally went to England. Now, the work of Bohm for the Bohm approximation is actually something which is intimately connected with these two other people. This is Jordan and Heisenberg. And Heisenberg, of course, as you know, starts quantum mechanics by thinking about these position or momentum and so on between a state n and another state m, and thinking of them as electric dipole operators. And there is the famous paper of Bohm, Jordan, and Heisenberg in 1926, which in the German is the 3-man paper. So at that time, actually, it was unusual to have 3 people on the authorship. Of course, times have changed. And so this is often referred to as the 3-person story. And it's in that context that the commutator actually first makes its appearance. It's actually in this paper, and it was a thing that was actually recognized by Bohm, not so much Heisenberg himself, but Heisenberg was his student, and Bohm recognized that what it really implied was that the position and the momentum don't commute, and you all know this story. But anyway, this is simply to set the three people. These are roughly what they looked like in the late 1920s and 30s when this work was done. The other person who played a big role in all this is Hans Bethe, who independently was actually doing some of the same work. And I won't go through all the details here, but let me just note that he was calculating what we call the oscillator strength, which is how much the electron couples to the electromagnetic field. And that has to do with, and then there are these so-called sum rules and so on. Again, the details, as I said, I don't want to go into here, but some of you will recognize. And the total oscillator strength was, of course, the number of electrons, because each electron acts as a full oscillator if you think about all the different transitions it can make, and you sum over all that. So, of course, you are going to end up with the capital Z, which is the number of electrons, so 26 in iron, or so on. Now, it's actually very interesting that Bethe was actually doing all this, and in fact, many others, including the Bohm work and so on, he really wasn't showing awareness of it. He was actually developing it himself, and he actually has some very interesting interviews which are available on the AIP, and he refers to it as though he learned that what he was doing all along was the Bohm approximation, for instance, without knowing it. So he actually compares with this famous story of the Moliere's gentleman who suddenly discovers when he's old that he has been speaking prose all this time. Okay. So the Bethe-Bohm approximation, which is why I always couple Bethe with Bohm for this story, for any electron atom or electron molecule scattering and so on, has of course played an extremely important role in both fundamental understanding of electron atom interactions and also in various applications and various places where it appears. So in the 1960s, of course, the development of lasers and synchrotrons, ion impact collisions, and there are a number of different theoretical calculations and techniques for it. And then the applications, there are many, many lab phenomena, atmospheres, of course, including other planets' atmospheres, plasmas, low temperature plasmas used in etching and microelectronics and so on, lots of radiation physics, biomedical applications. So there's a huge amount of this for both fundamental and for applied interest of electron atom scattering. And the Bohm approximation is sort of the natural to use right away, because in the first step, if the electron is sufficiently fast, it's as though it only weakly affects the atom. So this is what you study, and you do the first Bohm approximation, and often we don't go much beyond that. And the idea is that the first steps of incident radiation always lead to energetic electrons. So if you all can hear me, then let me just continue. So the first steps of incident radiation, even if it's X-ray radiation or gamma rays or anything, always lead to some electron being ejected, which then goes on, of course, to create its own ionizations. And this is therefore always part. Electron hitting an atom and ionizing it is always a part of any radiation, even if it was initially not an electron, and in fact, there's a nice rule of thumb that, for instance, if you take a 5 MeV, capital MeV alpha particle, which goes into, say, water vapor, it creates at the end about 100,000 ion pairs, that is an ion and the electron. And 50% of that will be from the initial alpha. But all the rest are from the electrons, which are then created, the secondary steps after the first collision. So electron atom in the Bohm approximation is something that we always have to deal with, both in the fundamental and in all the applications to these things that I list here. And again, as a nice rule of thumb, if you have a 1 kilovolt incident electron, or a 2 capital MeV proton, or an 8 capital MeV alpha particle, they're all roughly equivalent because it's the speed that comes in. And this 1 kilovolt is the one that I want to look at, that it turns out that beyond about 1 kilovolt, the first Bohm approximation actually works very, very well. in most contexts. And in a sense, it's because the electron goes by fairly fast on the atom, and whatever excitation or ionization it creates can be handled as a perturbation in the first Bohr approximation. But in the range between 100 electron volts and say 1 kilovolt, where actually there's a lot of interest, in fact, okay, so let me continue. So actually in the few hundred electron volt impact of an electron, or equivalently a higher energy, of course, for a proton impact or an alpha particle, these are all things beyond which the first Bohr approximation is perfectly fine. A 5 MeV alpha particle entering, say, some water vapor creates altogether about 100,000 electron ion pairs. By the time it's done, it has slowed down enough. And if you count, it turns out roughly 50% have come from the initial alpha particle, all the rest from the secondary electrons, which have been created down the line. So it's a good rule of thumb to keep that in mind at 5 MeV. And here is the equivalence. The same thing would happen if you had an electron impact with a few kilovolts and so on. But if you're below this, then it turns out that, of course, the first Bohr approximation itself is not enough. And but before I get to that, so this is simply a very quick one that I want to show, that the first Bohr approximation, the physics of it is that it's often called the plane wave, because the idea is that the initial incident particle you think of as described as just a linear momentum eigenstate, so plane waves, and so you think of the planes perpendicular to the propagation as the constant phase, or the same thing depicted here. So you have a free particle of some momentum h bar k, and you have the wave function, and this particular form was actually in Bohn's 1926 paper. Because it's very interesting that I just said that Bohr, of course, explains the hydrogen atom, and then there were all these oscillator strengths that Heisenberg was interested in. What is from the nth state to the mth state of the Bohr atom, what is the coupling to the radiation, which is expressed as what we call an oscillator strength. But Bohr was interested in the continuum part of the problem of electron scattering, and so Bohr was thinking in terms of a plane wave goes in, and because of the scattering it gets distorted, something gets added on, and then it expands out like spherical waves like this, and then the entire effect of the physics of the interaction is in this so-called scattering amplitude. And it is in that context that actually Bohr invents this idea of taking the modulus square of the wave function as the probability. So this 1926 paper of Bohr's is of course a crucial one, because both the commutator of x and p as IH bar and this interpretation actually are in that paper. They were not in Heisenberg's 1925 already. This is actually in Bohr's contribution. And no. The first occurrence is in the so-called Dreimanner Arbeit. I think I went over that quickly. And it is these three people. In fact, for a long time, everybody referred to it as the three-man paper. Because as I said, first of all, it's unusual to have three authors at that time. But Pascual Jordan, who was a postdoc of Bohr, Heisenberg was a graduate student of Bohr. And the story is that Heisenberg actually developed these things, and then he gave some notes to Bohr and went off on a 5-day hike. And Bohr, when he looked at it, realized that this was really like matrix algebra. Heisenberg hadn't recognized that, and then Jordan and Bohr actually worked this all out by the time Heisenberg returned. And so this is the famous three-person paper of 1926, and it is there for the first time that the commutator appears, and alongside the probability interpretation of the wave function, which is, of course, central to our subject. Incidentally, there's a little footnote. I don't want to go into details, but Bohr actually first wrote the modulus of psi. And then in a footnote at the end, I think in proof, he somehow changed his mind and said modulus of psi squared. So anyway, that's a little historical thing for the students to see that, of course, people were groping for how to understand this in the early days. And this is the famous three-man paper of 1926.
Heisenberg actually didn't recognize the rule of matrices.
No. Heisenberg did not know there were matrices, or what he was doing was matrices, and it's, as I said, these notes, Bohr recognized it, and Jordan, who was the postdoc, and they had worked it all out by the time Heisenberg came back from his hiking expedition. And so they wrote up the three-man paper. Incidentally, again, as a historically interesting thing, Bohr was actually very cut up that the Nobel Prize was given only to Heisenberg at that time. And so in a way, much, much later, when Bohr gets the Nobel Prize, it was actually a good thing, and in a way that he had lasted that long, because as you know, they don't give the prize posthumously. But Bohr had always felt that the commutator itself and so on were actually in his realization and his work, and it was not in Heisenberg.
When Bond finally got the Nobel Prize, Heisenberg is supposed to have said, "I'm so relieved."
Yes, Heisenberg was probably very relieved as well. But it is certainly said that Bohr used to get extremely nervous around October. And so yes. Okay, let me very quickly give you a feel for what the first Bohr approximation is, because it's part of the story. And of course, the first Bohr approximation is actually very simple. It says that if you go in with an initial momentum, you can think of it as a plane wave, and then of course you end up, and then think of that also as a different plane wave. It may have changed. So in elastic scattering, it doesn't change its magnitude, it just changes its direction. And it is basically the first order perturbation of the potential which is doing the scattering. So it's a matrix element of the potential between the two plane waves, which of course you recognize is simply the Fourier transform of the potential. So the first Bohr approximation is a direct readout, if you wish, of how the electron is distributed in the atom. Now, if you have a 1/r potential, it's easy enough also to see that this will go like 1/k squared, and in fact, it will depend only on the magnitude. If you don't have any angular dependence here, if it's isotropic, it will depend only on the magnitude. And there comes the famous Rutherford scattering. So in the cross section, which is of course the square of this, that has that famous 1/k to the fourth, which in velocity is like going down like 1/v to the fourth, and it shows this very sharp peaking at small values of k. Now, if it's a structured target, it's not a charge, a free charge, then of course you have to take the matrix element of this e to the I k dot r between the initial state, let's call that the ground state, and whatever state the atom may end up with. So there's the 1/k squared, which comes from this kinematics almost, and then there's the matrix element, and this is really what we call the oscillator strength. It's the amount by which the electron couples to the radiation, so it's like how much of the oscillator. Altogether, there is one electron, so that is where this famous sum rules and so on come, and that again I don't want to get into too much detail. But the first Bohr approximation, therefore, is really just as immediate first order perturbation between the initial and final states, both thought of as plane waves, undisturbed plane waves. Now, of course, then you can go further. You can go to things like the second Bohr and so on, where you go from some initial state to the final state, but now with two interactions. And of course, now you have to put in all kinds of intermediate states. And then comes the problem that in an atom, there is an infinite number of intermediate states, even for the hydrogen atom. And these calculations are so much more, almost qualitatively more difficult than doing the first Bohr. And in fact, most calculations, when they just say Bohr approximation, are actually in the first Bohr approximation to this day. There are very few who actually spend the time to do a second Bohr or some more complicated thing. And generally speaking, the first Bohr approximation works very well in electron-atom interactions if the electron has energy larger than 1 kilovolt, and you can basically say that it goes by so fast, so to say, that it only weakly perturbs. So it's enough to take just the first order perturbation, and that is why the first Bohr is the one that most people use. Now, however, for many, many applications, in the few hundred electron volts, so you're not quite at that 1 kilovolt, and this is where really a lot of radiation physics, including biomedical applications and so on, lie. For many of them, it is not enough to stop with the first Bohr. And then various things have been done because a full-scale second Bohr calculation is usually very complicated. And there comes Bethe again. Bethe actually gave some sort of tricks to get around it. So we often refer to it as Bethe-Bohr or a binary encounter Bethe, and all kinds of names that come up. And there are various scaling methods that are used and so on. So in the general context of electron-atom interactions, there's an awful lot of details of this which have been worked out. That's not what is of interest for me today. But let me just show that, for instance, actually a few years ago, we wrote in RMP, a Reviews of Modern Physics article on that with experimental colleagues from Japan and from Australia. And so really, for many diatomic small molecules, carbon dioxide, which is of course an extremely important greenhouse gas here, and it also dominates the atmospheres of Mars and Venus, and then all these nitrogen oxides, which are also pollutants, carbon tetrafluoride, which is used in etching, so low temperature plasma etching, and it plays again a role in global warming, the carbon chlorine counterpart, and of course water. So the radiation dose for all biological cells is dominated by water, because 70% or more of our bodies is essentially water. So that's the default molecule when we are using a model for radiation physics in treatment or in diagnostics and so on. So now, just as an example, I just want to show you what the state of the art is that, of course, we reviewed in this. And that is, for instance, this is in helium. In electron impact, note particularly this range from 100 eV to about a kilovolt, which I said is more complicated. But these various Bethe bone and various names, actually, this is the state of the art today in our calculations of the cross sections. This is electron on carbon tetrafluoride, which is a greenhouse gas as well. And so this is roughly where and the kind of accuracies that we can calculate. I'll just skip over this. Of course, carbon dioxide is the thing that we think about. And again, this review article surveyed some of that. But let me move on, because I want to get to the meat of the story, and that is the charge transfer between a positive ion and a neutral atom at high speeds. So here is electron capture, or of any light particle with or without radiation. And then there is radiative capture, of course. The electron can be captured and radiation comes out to conserve the energy. You can capture into a highly excited state, we call them Rydberg states, or into the continuum. You can capture at high velocities into the forward direction. And the single scattering was recognized very early, depends on the high momentum pieces, and that first Born term drops off as the speed to the 12th power. So in high energy electron going by an atom, the first Born approximation, or when you have an ion coming on an A and capturing an electron, the same story, that this drops off as V to the minus 12. Now here comes the first part of the story for this afternoon, and that is that L.H. Thomas, I think many of you will... Non-relativistic, yes. This is non-relativistic still. So L.H. Thomas, whose name many of you will know, is associated with various things I've sort of listed here. L.H. Thomas had a very interesting paper in 1927, where he said that when an incident ion hits a neutral atom, whose electron, let's say, is schematically shown like that, this is the A's nucleus and maybe other electrons, then capture is probably going to require a double collision. And his point was actually very simple. In the physics, as you can imagine, if a big cannonball comes and hits a little ping pong ball, the ping pong ball will simply shoot off into the forward direction. There's no way that it will get captured. So what Thomas basically argued, that it takes two collisions. So the big ball must hit this light electron, scatter it, and then that electron goes and scatters from its parent nucleus of this M2, which then scatters it at well. And what Thomas worked out was that both these scatterings at 60 degrees will result in this electron now having both the direction and the speed to match the incident B plus, to be captured by it. So that they're going along in parallel, so to say, and then they can get captured. So Thomas had this sort of intuition that there should be a double collision, which leads to this capture into the roughly forward direction. I'll come to a little more detail in a minute. And he worked this out with classical physics and came up with the idea that this classical double scattering will drop off like the velocity to the 11th power of the incident velocity. Whereas the first Born approximation actually drops off as the 12th power. So here's an example where the first Born approximation is not 0 as you calculate it, but certainly you'll all recognize, of course, that this is going to dominate at some point over that at sufficiently high V.
The 60 degrees is to first order in some mass ratio?
It's not a mass ratio at all, no. You'll see it in a minute, right? But the 60-degree kinematics, I'll get to, of course, but this was Thomas's model for a double scattering, which is required to have this process take place, and in particular that it'll drop like the 11th power. Now,
Higher order terms are even?
I'll come to the higher order in a minute, yes. Now, in the radiative capture, the nucleus is essentially a spectator. So if the electron gets captured and radiation comes out, incidentally, that's also part of these interests. And I just put this in because Oppenheimer was working with Bohm at that time, and they worked out this roughly at the same time as you see. And this has been worked out in various other contexts as well. For instance, a proton hitting the hydrogen atom, and then you have the ion-ion interaction. But let me just go back to this Thomas result, that the velocity to the 11th power is how it goes. And when you calculate, however, in first Born approximation in quantum mechanics, which was done around 1930 by these people, then it actually drops. There is some angular dependence as well, but let's take L equal to 0 as the lowest possible. It still drops off at least as the 12th power. And of course, this will always dominate over that 12th power. Now, it is said that even Bohr was astonished by the Thomas result, and many of them just discounted it. They said this is just a classical mechanics, classical picture that Thomas has worked out, and there may be some subtle interference effects or so on, and the quantum mechanical result is what is correct. It's really remarkable that it took a long time, because 1955, from then, that a PhD thesis, it's still unpublished, by a person called Driscoll at the Carnegie Institute, he took seriously this picture of Thomas and worked out the second Born approximation as what would be needed if you had to have two scatterings, as in that picture that you saw on the previous slide. And indeed, that one gives you the v to the minus 11 dependence, which today has been, of course, confirmed experimentally, theoretically. Again, I won't go into the details of that. A lot of that was actually done by this group that I was a postdoc with, Larry Spruck and his associates. And the second Born actually, therefore, now we know quite well, both experimentally and theoretically, actually dominates over the first Born. Now, the question that was just asked, you might ask immediately, what about the third Born or the fourth Born and so on? And that convergence of the Born series is still an open question in general. In fact, it probably doesn't converge. But what has been done by these people is that they put certain bounds on what all these other higher order terms can amount to. And they actually showed that actually the leading term is indeed the one that the second Born gives. And that goes like v to the minus 11. And so, and experimentally as well, that has been measured, including details, which I'll now get to, about the angles and so on that are involved in response to that question as well, that it takes two collisions, therefore. So that's why the second Born, there's an interaction here with the V, there's another interaction here.
Minimally two collisions.
Pardon?
Minimally two collisions.
Yes, actually 2 is the dominant, because the third and higher order terms have been shown to be less than the second term. So the sum of all the other terms is still dominated by the second Born. And the second, and the reason for that collision, you can actually see almost from simple kinematics. And this is why Thomas's classical intuition had worked and why he had worked it out. And I'll just go through this a little bit quickly, but it's fairly easy to understand. It's actually very simple conservation laws of momentum and energy that you apply. So here comes this heavy particle MB, it hits this little electron M, and of course it gets deflected. The electron gets deflected like that, and clearly the heavy particle is only getting deflected very slightly from its forward direction, and that's what I've shown here, and it goes off with slightly smaller velocity, but not all that much smaller. But now this electron goes and collides with its parent nucleus, which is the MA, which is of course much heavier than the little m, and then it gets turned around again. And when it gets turned around, again through some angle, then if you can match both the speed and the direction of this with what has happened to the MB particle, then of course they can get picked up. So that is the idea of this double collision, which Thomas had intuitively thought about and worked out in classical terms. And indeed, if you look at the kinematics and you look at also the calculations, it turns out it's not very difficult, that it actually emerges as the inverse cosine of a half, and that is where the 60 degrees is lying, that both these angles, this psi and then of course this angle, are 60-degree impacts. So the big particle ion comes and hits this electron, makes it go at 60 degrees and hits its parent nucleus, which turns it by another 60 degrees, and then it lines up to be captured by that initial particle B. And you can work out the total cross sections and so on. And if you do this quantum mechanically, in fact, again, I won't go into the detailed argument here, but the capture of that double capture of that capture actually is some kind of thing which finally, when you look at the powers of velocity involved, gives the 1 over v to the 11th. So the second Born approximation applied to this verifies Thomas's basic classical intuition. And in fact, it verifies in great detail because, for instance, this angle clearly is going to be very, very small because the big particle is only going to be slightly deflected in that collision with the electron. And if you look at it, it's about 1.6 seconds of arc, minutes of arc. And this also has been experimentally measured. And then even more details, which again, I won't get into. There is a cross section which actually shows a cusp. So all the details of the Thomas method, and as worked out in the full second Born calculation, actually are verified in experimental detail as well. Now, I have a few minutes, but let me just mention a couple of topics. There are gravitational analogs of that, which might become actually quite interesting, particularly now with some of the gravitational wave stories and so on. And of course, the gravitational analogs has to do with the capture of a planet by a star. So let's say a star goes through our solar system and it might capture one of the planets. Okay. Now, of course, there's a simple translation that all of us know how to do, and you can actually, again, calculate many of these. And of course, this hasn't quite been experimentally seen, but something very similar you can do with heavier particle impact. So if you have, say, a proton hits a methane molecule or the one before that, CH3, and then it captures one hydrogen now, not an electron. It captures an hydrogen and becomes H2 plus. So H2 plus is what comes out. And in that case, if you work out the kinematics, instead of the 60 degree, you get this 45 degrees. And this has also been both experimentally and theoretically verified. So we know that this double scattering mechanism of Thomas, which he anticipated in 1927 almost intuitively, is what is required to be capturing a light particle by a heavy particle going by in a neutral atom. And that is why the second Born approximation dominates. So that's the essential physics of this. And now with that, in the last couple of minutes, let me return to what is the connection between this and this rescue of a person at sea, or turning your ship around so that your guns can fire on the shore in the opposite direction, that Williamson-Butakov turn that I started with. And here, this is again what I said, that if you're going along like this, you maintain the same speed, but you make a turn, and when you're going at 60 degrees, then you rapidly turn in the opposite direction, and you end up with the same speed, but facing in the opposite direction at that point. Okay. Now, of course, this is really two circles, if you think about it, osculating circles. They sort of meet here, and this is the tangent line to that. And so you do about a 1/6 of a turn before turning the wheel hard in the opposite direction. So we end up finally traversing basically the diameter of that one of these circles to end with reversed velocity at that point. Now, that is the connection. So there is this 260 degrees involved in both this very simple classical thing and the 60 degrees I showed you in the previous, which is involved in the quantum mechanical scattering as well. Now, of course, you should ask immediately, why does this work? First of all, in quantum physics, there are no trajectories like that. But then the key to that, of course, and particularly for the students to appreciate, is that really what is going on is simply conservation laws of momentum and energy. And that is all that is really being put, even though when we write all these and work out with diagrams to aid our imagination, really what is happening in that analysis that I just did before, in this analysis, was simply to apply the laws of conservation of momentum and energy to end up with this situation. And so those laws of conservation are just as good in the quantum context, and the trajectories and so on are just aids to our imagination. But so even in classical mechanics with Galilean relativity, and it's always only the conservation laws which are going in when we do these calculations. And so they are valid throughout, down to each individual event at the molecular level.
So the can't we think about path integrals and dominant path is this? Think in terms of path.
Yes, if you want, the classical trajectory, yes, is the dominant part, yes. But again, what I want to emphasize is that the trajectory itself is not so crucial. In fact, quantum physics, in a sense, doesn't have trajectories. But really what is involved are just the conservations of momentum and energy. And that is why it works. And this is why, in a sense, Thomas's intuition is sort of borne out, even with our, now see, you can almost not give a talk without making a pun on bone. Okay, so anyway, so that slipped out without having been planned. And there are indeed many, many puns in the title about the second bone approximation in this story. Now, one last thing to end with is that my son is actually a yachtsman. And he, of course, pointed out to me that what I was talking about powered ships and so on, has to be modified when you think in terms of a sail ship, which is what he's interested in. But then again, there is a turn that they all have to study and pass exams in and so on, that if you want to turn your boat around, say somebody falls overboard, you do this turn. Again, there is a double turn involved in that. But here, one critical thing that you have to keep in mind is that at all points, you don't want your sail to catch the wind in the wrong direction, because then the thing that the sail is attached to will sweep across the deck and it can even sweep you overboard. So at all points you want to maintain, and that's something which, of course, for the powered ships that I talked about doesn't apply, but it is very interesting that actually they learn this Williamson-Butakov turn in when they have to take the tests for sailing, and that is the connection.
Fishermen.
Yes, I'm sure they know about it too, exactly. So with that then, this is the story that the second bone approximation actually dominates over the first bone, at least in this charge transfer at high speeds, and it's both quantum mechanically true and the classical intuition of Thomas is sort of borne out, again bone. And so this, incidentally, there is a word apparently for this, that you want to avoid having that big boom come across the deck and sweep you into the sea, and they call it a jibe. So you want to avoid this sort of thing, this word called a jibe. So that is part of the story for a sailboat, which is, of course, somewhat different from a powered boat that I was talking about. But that's the story of the second bone dominating in a real context, and you can sort of understand it in these classical pictures. Okay, with that, let me stop. Any questions?